The distance between them is small compared to the size of the plates, so yeah.
So you can use the sigma over epsilon so not?
Yep. Because I haven't mentioned anything, there's nothing in between the plates except for, I was about to say air, but except for nothing, there's nothing between the plates. So with nothing between the plates, then it is sigma over my electric field strength, sigma over epsilon sub naught. So we have a sigma of 3.6 times 10 to the negative 7th, and that would be coulombs per square meter, divided by epsilon sub naught, 8.85 times 10 to the negative 12th, coulomb squared per Newton meter squared. Meter squared will cancel out, one of the coulombs will cancel out, and we're left with some number, if someone would be kind enough to do that.
4.07 times 10 to the 4th.
Newtons per coulomb. Now, before, and I think this was part of a transition bit we did last time, I know that the voltage, I know that the electric field is the negative gradient of the voltage. Or in a one-dimensional problem, we'll just simplify it down to negative dV dx, since I could to write it as a partial would probably be more accurate, but I only have one variable anyway. If I multiply both sides by dx, I get E dx is equal to, or negative E dx equals dV. Integrate both sides. My electric field is, I got sloppy there with units. Sorry, with notation. Slightly less sloppy. And so if the electric field is constant and in the direction that we're moving, which explains why I got rid of the vector symbols, I have negative electric field strength times delta x is equal to delta v. Sometimes refer to this as the ED equation. If we think of, I have delta x there, but if you think of d as the distance between the plates, then you have ED. So I know the voltage, I know the electric field, so what's the distance between the plates? Or how would you find it?
Your voltage over your electric field.
And we end up with, the voltage was 12, my electric field was 4.07 times 10 to the 4th. That's 12 volts, and that's newtons per coulomb. And we end up with
2.95 times 10 to the negative 4th.
units.
Meters.
So we're talking about 0.3 of a millimeter apart.
Could you theoretically keep increasing the distance as long as you have enough voltage?
But if
Like,
you
would it
have it,
still work?
as in still,
Still work, yeah.
if you have enough, so if it's connected to a battery, yeah, at some point, the infinite plate approximation is not going to be valid. But
Well, I just meant like a capacitor in general, or whatever, could you keep increasing it? Is like the distance related to how much voltage you're applying, like whether it works or not?
it will still, well, let's do that more specifically math-wise. In theory, yes. At some point, the capacitance is gonna look a whole lot like it's not there. Because when you did the lab and you found this 2 weeks ago, you found the base capacitance. you put the plates far enough apart, it's gonna be within a statistical fluctuation of that.
What if we just had like a very large amount of voltage we had access to or something though? Could you just keep going?
Yeah.
Okay.
There's also, another measure, which we don't really touch on, but there's some nice videos out there. I believe I mentioned, or maybe it was the other group, the dielectric strength. That you have enough voltage, yeah, if I got, let's say, a huge amount of voltage, I got my plates this far apart, I can measure capacitance, fine. I get closer and closer, at some point, they'll be so close that, it's such huge electron buildup that it's gonna spark through. So there is a point at which whatever's in between them is going to basically break down. So with it, the large enough voltage, yes, you can get farther apart, but there's only so far you can get close before your capacitor is, in essence, useless.
Or it's basically just like it's connected.
Yeah. So now, the math bit. So I know that the capacitance is that charge over the voltage. It is a positive number. In a capacitor, I'm gonna have a charge, positive charge on one plate, negative charge on the other. They're basically the same magnitude, just one's the opposite sign. So we only care about the positive plate, or this is a positive number, however you want to justify it to yourself. I know that the charge on the plates is sigma times the area, so the surface charge density times the area, over my voltage. But I know my voltage is just going to be E times the distance between the plates. Again, we're assuming, so this is always true. And this is parallel plate capacitor. I know my electric field for a parallel plate capacitor is sigma over epsilon sub naught. And so this becomes sigma A over epsilon naught D. Sigmas cancel out, and I'm left with epsilon naught A over D. So the left from 2 weeks ago. Constant, the area of the plates, the overlapping area of the plates, and the distance between the plates. So in theory, as D gets bigger, the capacitance drops off, but as long as you're not an infinite distance away, or if that's infinitesimally small, if that's infinitesimally large, that doesn't really quite make sense. If D goes to infinity, the limit of C is 0. But this does offer us a way of adjusting if we throw a dielectric into it. Because if we have nothing in between the plates, then we're using free space. And so we use the permittivity of free space. However, if we put a material in between, the kappa comes into it, or we could write it just as epsilon A over D, and that's the permittivity of the material. But epsilon over epsilon sub naught is equal to the dielectric constant, which is supposed to be a kappa dielectric constant. And so this becomes kappa epsilon naught A over D.
What's epsilon versus epsilon naught? What are the differences?
The subscript 0 is telling us it's free space. That's the 8.85 times 10 to the negative 12. This is if I've got some medium in there that's not emptiness.
Okay.
So for air, and one of the reasons why I earlier said air, kappa's really close to 1 for air versus the vacuum of space. Paper varies, but it's generally in the order of 1 to 3 or something like that. Or based upon something like the student results, 0.5 to 50,000.
Air is close to vacuum though.
Air is close to 1.
Vacuum is 0.
Well, vacuum, this would be epsilon sub naught, so it'd be 1.
So vacuum and air are basically the same.
Yeah.
Okay.
It's a measure of how it is affected by an electric field. So delving into that, so I now have my parallel plates here. I put a dielectric in between. And again, I think I did this already last Friday or 2 Fridays ago. I have an electric field, and that's my positive and negative plate. I have an electric field going off to the right here. It is going to polarize because this is not, the material I put in here is not conducting. I'm not gonna have charges really moving, they're gonna shift this orientation, so I will have, well, if I have an electric field going this way, it's gonna pull the electrons in that direction, so I'm gonna have a whole bunch of little tiny electric fields going in the opposite direction. If it's hooked to a battery, my voltage stays the same. My electric field inside here, let's see, voltage stays the same, my total electric field will stay the same. Let's go through the steps. I stick the dielectric in there, still connected to the battery. The capacitor is still connected to the battery. So my voltage stays the same. So it's still capacitor connected to my DC power supply. Add dielectric. My voltage stays the same because I'm connected to the battery. Stays constant. Because my voltage stays constant, think of this equation over here. I haven't changed the distance between the plates, that's constant, therefore my electric field, total electric field strength stays constant. And dielectric, since, let's use a lowercase d, since d doesn't change. My electric field strength, total, is the same. But I have a whole bunch of electric fields. If my total stays the same, I have a bunch of tiny electric fields going in the opposite direction. The only way that my total electric field can stay the same is if the electric field from the plates goes up. Because I have a whole bunch of negatives in here, I have to offset that. So my electric field will, on the plates, goes up. So the total electric field is constant. The electric field from the plates goes up. Therefore, my surface charge density goes up. Therefore, more charge stored. There's probably a shorter way of getting there, but figure that out on your own. So by adding the dielectric, I can store more charge for the same potential difference, and thus increase the capacitance, which matches what we have over here. The fact that since kappa is going to be 1 or greater, 1 if it's free space, more than 1 if it's anything else, any other insulator, then that goes up, which indicates if everything else is the same, my capacitance will go up. Questions here?
Regarding the lab from last week,
Okay.
with the tables in dealing with ideal and experimental, some of the things that we had as experimental, we assume as ideal, right? like, for example, the measured capacitance in nanofarads of the.
Oh,
Yeah. I was-
of each individual capacitor?
Capacitors, yeah.
Yeah, well, yeah, we assumed that that measurement was correct.
And then the same with the power supply, like, do we use the measured power supply as the ideal voltage?
Yes.
Okay. Not just what we had the power supply set at, what we actually measured at.
What you actually measured.
As the ideal, so really the only ones that we're gonna be, calculating based on something would be like the ideal capacitance, I guess, cause then you can just add like two of them together or
Yeah,
something.
the equivalent capacitance.
Yeah, that's what I meant, yeah.
Yep.
Equivalent capacitance, everything else is just copying numbers.
Yeah,
We
well,
gotta-
no, you just copy a number. We assume that what you measured directly, as far as the voltage is concerned, was accurate, and for each individual capacitor was accurate.
Yeah, so you copy those over from both the measured to the,
Yeah.
yeah.
But then like.
That's voltage of the power supply, not voltage across the capacitor itself.
Yeah, so then the charge of the electric capacitor, or like how much charge it holds, and then the voltage across that specific capacitor, we can use based off of like, or we can determine based off of like some of this theory. Because like, if they're in series, is it in series the voltage stays the same across, or?
Not across each individual one. We'll get there.
Okay.
We'll keep looking for a clock. Yeah, we'll get there.
Okay.
Bill, do you have a follow-up question?
I don't remember what it was, 'cause I had the same questions.
All right.
When I was trying to do the lab, yeah, but I think there was a little bit more that I just needed clarification on, but I don't remember what it is right now. I'll figure it out.
All right, hopefully it will
Yeah.
answer it in the regular course. Here's desperate need of it, okay, yeah, no, I'm aware. The lab for tomorrow, I haven't uploaded it yet.
No, in the lab for this.
Oh, the lab for last week?
Yeah.
Oh, okay, I guess I need those two labs. I'm sure there's more. All right, so all of this was, well, not all of it, good chunks of this, especially this interpretation right here. The voltage stays constant, assumes that it was still hooked up to the battery. But if it's not. So what I do is I'm gonna set this up, I get the capacitor charged up fully, and now I need to disconnect the battery. We will assume that for board problems and things like that, that disconnecting the battery is done perfectly. If I disconnect it too slowly, what's gonna happen is that there's gonna be a small little spark there, and you're gonna lose some of the charge on the plates. So you have to break the connection very quickly. I've tried, I am not fast enough. We're gonna break the connection quickly, no spark, no loss of charge. And so I charge this up, it's now not connected to anything. And once I do that, if it's disconnected, the charge is fixed. So if disconnected, if power supply is disconnected, charge is charge on plates is fixed. Because if I disconnect it, the charge is nowhere to go. Again, we're in our nice ideal world, there's no humidity, nothing's bleeding off. If there's no place for the charge to go, it's just gonna stay there. Now, no matter what I do, assuming I don't ground the plates, now no matter what I do, my charge is fixed. So if I take my parallel plates and let's say I double the distance between them. Well, if I double the distance between them, I cut my capacitance in half. Which is why, and you noticed this before, not that we disconnected it, but the closer the plates are together, the higher the capacitance. As you put back more and more sheets in between it, the capacitance should have lowered. And the potential difference across the plates is changed, because if my charge is fixed and my capacitance gets smaller, the voltage has to increase.
Yeah.
So I now have a larger voltage between it. So why don't we start out with, I have some initial voltage here, I have some initial capacitance, some initial area, the distance between them is some initial distance. And nothing in between. I have some electric field. This way I have it set up. Once I connect it, I'll have an electric field going this way. I'll have some initial charge, and I'll have some initial electric field strength. So the first thing my capacitance, initially C sub 0. My electric field strength total, E sub 0. My electric field strength from the plates, E sub 0. My charge, Q sub 0, and voltage, V sub 0. So this is just how I've started the problem. I'm now going to manipulate it, and let's just play around with what happens. I keep it connected and add dielectric with a dielectric constant of 2